In question 1, we want to compute these 4 logarithms. Starting with part A, what is log base 4 of 16? This is asking 4 to what power gives us 16. It's kind of nice to view it as an equation, so maybe I'll call this x and set it up as 4 to some number is 16. Well, I know that if you square 4, you get 16, and therefore the answer is 2. For part B, log base 5 of 1, what does that equal? So 5 to what power gives you 1? Well, any non-zero number raised to the power of 0 is equal to 1. Therefore, the answer here is 0. So with all of these, the answer is going to be the exponent. What about log base 2 of 16? What does that equal? So I'll call it x. So 2 to what power is a 16th, 1 over 16. Anytime I see a fraction like this, and I'm working with logarithms, I know the answer is going to be negative. And what I'm really thinking is, oh, well, forget the fraction part, but look at the 16. I know that 2 to the power of 4 is equal to 16, but if you make that negative 4, it puts the 16 into the denominator. Therefore, the answer here, it's not positive 4, but it's negative 4. Okay, the last one here is log of 0.0001. Now, just for emphasis, this means log base 10 of 0.0001. So when it's not written and you see log, we're talking about log base 10. Okay, so this is equal to some number, I'll call it x. 10 to what number gives 0.0001? Base 10 is nice because we're talking about moving the decimal point. So how many times did we move this? We moved it 1, 2, 3, 4 times. Because the number became smaller, I know it's going to be a negative 4 instead of a positive 4. So here the answer is negative 4. In question 2, we're going to expand these expressions using properties of logarithms. Starting with part A, this is log base 9 of 81 times z. So I see a product, and I know there's a rule that says if you have a product inside a logarithm, you can rewrite this as a sum. So it would be log base 9 of the first thing plus log base 9 of the second thing, which is the variable z. And okay, I can't simplify this anymore. Now this, though, I think we can reduce a little bit because 81, I believe, is an integer power of 9. So when I look at this piece here, 9 to the power of something equals 81, and I know that's 2. You square 9, you get 81. Therefore, this whole thing here is just the exponent 2. So this is really 2 plus log base 9 of z. And this is the completely simplified answer. In part B, okay, this is log base 10, or just log of, and I see a product, I see an exponent, but the first thing I notice is we have a fraction here. So if you multiply, it becomes addition, but if you divide, it goes to subtraction. This is equal to log of xy squared minus log of 1,000. So again, this main fraction split up the numerator and the denominator. When I look at this piece here now, I see I have a product, and I can apply this previous rule to this part. I can break it up as a sum. So this is log of x plus log of y squared minus log of 1,000. Now there's another thing I'm seeing here in this expression. I can't reduce this. This I think we can reduce. Log of 1,000. 10 to some power equals 1,000. And that's going to be 10 cubed. 10 cubed is 1,000. So this whole thing here can just be re-expressed as 3. But also, this thing here, we have y to the power of 2. We can take this 2 and bring it to the front of the logarithm. I'm going to do both of these things in one step. We have log x. That can't be simplified. But there's a property of logarithms that says if you have a power raised to the entire thing inside the logarithm, you can place it in the front of the logarithm. And then instead of log 1,000, I'll just put 3. And this is the completely simplified answer.